Okay, now we are going for fourth online lecture. This is the almost most probably last lecture for you. So in this lecture we'll try to complete all the things. So here first we will try to discuss on the capacitor. This capacitor is a passive element designed to store energy in its electric field. Is the definition. And a capacitor consists of two conducting plates separated by an insulator. So you see here, this is the two charging plate and it is the charge conducting plates. It is the negatively, it is the positively charged. They are separated by a distance d and separated by the insulating materials. So it is the construction of capacitance. In this way, capacitance can be grown. So the capacitance formula is given C equals to epsilon A by D. So epsilon is the permittivity and A is the area, D is the distance. Okay, C means here capacitance. So charge stored in capacitance is Q equals to CV. Is the another equation for calculating the charge in the capacitor. Q is the charge Q equals to C multiply V. V is the voltage, C is the capacitance. So unit of charge is coulomb and unit of capacitance is farad. We can represent by capital F is the farad. Now we are going to determine how to calculate the series and parallel equivalent resistance capacitance. So here you see that some capacitors are connected in parallel, but their total equivalent capacitance is calculated as C1 plus C2 plus C3 plus C4. It is just similar as the series operation of the resistance. That means here parallel capacitors, in the case of parallel connection of the capacitors, the equivalent capacitance C equivalent equals to C1 plus C2 plus C3 plus C4. It is just opposite to the resistor. We see that it is opposite to the resistor operation. That is, it is the parallel connection but gives the our series resistor equivalent circuit like. Okay, we know that for series equivalent resistance it is the plus R1 plus R2 plus R3 plus this way. So it is in the case of capacitor is just opposite to the resistor operation. So when capacitors are parallelly connected, they must be added C1 plus C2 plus C3 plus C4. Very simple, that is addition. Operation is occurred for parallel connection. When series connection is occurred, then it is like the parallel operation of the resistance. You see, parallel operation of the resistance like. Okay, so 1 divided by C equivalent equals to 1 divided by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4. You see, these are the capacitors connected in series. So their equivalent capacitance is this. That is similar to our parallel resistance operation. Now we are going for solving a math relating capacitance. Practice problem 6.6. So you see there, two capacitors are connected in parallel, and you see these 60 and 120 microfarad connected in series, which are parallel with the 20 microfarad. So now if we want to simplify it for the solution part, now we are going to solve it. So if we simplify, you see these two parallel capacitors equivalent must be added 50 plus 70. We have seen that is for parallel it must be addition 70 plus 50. Now we see for series part 60 and 120 it must be parallel like 60 multiply 120 divided by 60 plus 120. So we have got this 40 microfarad. Now you see this and this is the now parallel connected. So for parallel operation we know it is should be additive 20 plus 40. This 20 plus 40. So that is the our last circuit here. Now they are connected in series, so it must be this parallel like 120 multiplied 60 divided by 120 plus 60 equals to 40 microfarad. That is our answer. C equivalent is 40 microfarad. Now we are going for solving the another math, that is the example 6.7. In this example you see that for the circuit in figure 6.18, this is the 6.1 figure, find the voltage across each capacitor. That means we have to find out the voltage across each capacitor. This is the V1, V2 and V3. Since they are connected in parallel, so voltage would be same, that is V3. So we need to determine V1, V2 and V3. So we can simplify for the solution as this line. Okay, now you see if you add these two capacitors in parallel connection, that is 40 millifarad and 20 millifarad must be additive because they are connected in parallel. So we have seen here two capacitors are added, that is 60 millifarad. Now see this capacitor across voltage is V1, that is V1, 13 and microfarad across voltage is V2, and this equivalent across is V3. So our target is to determine V1, V2 and V3. Okay, first we need to determine total equivalent capacitance, C equivalent. Since they are connected in series, so our equivalent capacitance calculation must be as the parallel operation of the resistance. 1 divided by C equivalent equals to this 1 divided by C1 plus 1 divided by C2 plus 1 divided by this 60 millifarad. Ultimately you are getting 1 by 10, that means C equivalent equals to 10 millifarad. Now total charge Q equals to C equivalent multiply V. We know Q equals to CB. So here total charge Q equals to total capacitance multiply V. Total voltage is 30 volt given and total equivalent capacitance is 10 millifarad. You see 10 into 10 to the minus 3 farad. So ultimately you are getting 0.3 coulomb. Coulomb is the charge unit. Now since Q equals to CB, so we can say V equals to Q by C. So if we want to determine V1 must be equals to Q by this C. C means here 20 millifarad. Here Q is just like the current. We know for series connection current is same. For this series charge would be also same. Okay. So here Q equals to here CB. So Q equals to CB. So B equals to Q by C. So using this formula we can say V1 equals to Q by C1. C1 is 20 millifarad, you see. So we have got 15 volt